A galvanometer is a sensitive device for measuring current. Assume that when the galvanometer is connected to a battery as shown and current is flowing counterclockwise, this leads to the needle in the galvanometer being deflected to the right. We'll use that as a reference in order to draw the correct deflection in this situation below. So when current flows through the galvanometer to the right, the needle is deflected to the right as well. In the situation below, the galvanometer is connected to a coil. And in this case, we're going to vary the magnetic field that's flowing through that coil. The way we'll do it is by moving a bar magnet closer to the coil. Now, why should this change the flux through that coil? Let's draw why that would be the case. In order to analyze what's happening inside the coil, we can do a drawing of the before and after. Now, before the magnet is moved closer to the coil, we can draw the magnetic field lines that would leave that north pole of the magnet. If we do, we might find that in this case, a small number of field lines will actually penetrate through the loop of the coil. But when the magnet is moved closer, we want to see how the flux through that coil is changing. And now, when it's closer, there may now be more field lines penetrating through that coil. So the first step of analyzing this is figuring out in what direction is the field going through the loop in the first place. So there will be a magnetic flux is flowing to the left initially. Through the loop or through the coil. Now in the after picture, we see that the magnetic flux is increasing. To the left. And so Lenz's law says that a current will be created in order to oppose the change in magnetic flux. So what kind of induced magnetic flux would counteract the change that we see in this situation? Well, what we would want is we would want a new magnetic flux to be created. And that new magnetic flux needs to flow from left to right. It's called B induced. And this way, if we add the induced flux to the flux created by the magnet, they could cancel out and equal the original flux. Our last step is to figure out what kind of current flow in the loop would cause this type of magnetic field to be induced. Would it be counterclockwise or clockwise? For that, we would use the right-hand rule. We want our fingers to curl around this loop. We want the fingers to be curling through the center of the loop. And if we're using the right hand, we see that the thumb now points down. So that is going to be the direction of current. So that will give us the direction of the induced current. Now we can go to our picture of the coil and show that current is flowing clockwise through it as that magnet is moved closer to the coil. This will cause the galvanometer needle to be deflected to the left. But only while the magnet is approaching. If the magnet remains stationary, then the current will cease and the galvanometer will not be deflected. We'll only see the deflection when the magnetic field through the loop is changing. We'll only see the deflection when the magnetic field through the loop that's created by the magnet is changing.